All right. First, I guess a lot of people have questions about problem 3 on the homework. Raise your hand if you had problems with that one. Okay. Hold on one second. All right. All right, let's go look at it. So, I guess the issue for a lot of people was just a misunderstanding of the instructions. Well, I guess, yeah, number 3. So number 2 was fine. Did anyone have problems with number 2? Or it was just number 3? Okay, so number 3 says, describe the operation of the circuit in problem 2 without removing or changing any components. Devise a plan to discharge the capacitor after the switch opens. So a bunch of people said that they thought that that meant that they basically couldn't do anything, but that's not what it means. It means you can't remove or change any of the components. You can add components, but you can't remove or change any of the components. So basically, I think how many people had that misunderstanding? Okay. I'll have to work something out because I figured that it might have been clear enough that you could add components. I'm going to tell Abraham that if you came up with a good enough reason why it doesn't discharge and like you gave an explanation, that you'll get the points, so that the people who didn't know they could add components still get the points. However, let me just discuss why it doesn't discharge for those of you who don't know. So let me draw this on my paper real quick. All right. So basically, this is the circuit I'm looking at. Right? So my switch closes at time t equals 10 milliseconds, and my capacitor starts charging, right? It starts charging based on the charging equation, which is going to say the voltage across the capacitor, let's call that Vc of t, that's equal to my 12 volts times 1 minus e to the minus t, but it's going to be minus 10 milliseconds, right? Because that's when it actually starts charging. And then that's going to be over tau. In this case, my tau is equal to 2 microfarads times 1.5 K. So basically 3 milliseconds, right? So I would put 3 milliseconds. And that would be the equation for when it's charging. Everybody's fine with that? Okay, so what I would get is basically something that looks like this after 10, let's say that's 10 milliseconds, and it's going to take roughly 5 time constants to charge up to 12 volts, so somewhere out here at like 25 milliseconds, 15 milliseconds later, it should be pretty much all the way there, right? And then, I think in the problem, the switch opens again at 35 milliseconds, right? So then I would draw an arrow that looks like that, signifying that the switch opens at 35 milliseconds. Okay? So the question is, why doesn't my capacitor start discharging at 35 milliseconds? And for those of you who know, I'm going to explain it anyways, but for those of you who don't know, everyone remembers that the current flowing in a capacitor, we said it's equal to C times the rate of change of the voltage across the capacitor, right? Well, I can rearrange this equation by dividing by C, and I get that the rate of change of the capacitor voltage is current over capacitance, right? Well, if my current is 0, then that means that the voltage of the capacitor can't change, right? Current needs to either be flowing into the capacitor to charge it or out of the capacitor to discharge it. Okay? When this switch opens, there's nowhere for these charges to flow, right? It's an open circuit. Okay, so that's why the capacitor voltage stays put even when the switch opens right here. All right? So in order to fix this, you have to add a path. You have to give it a path for charges to flow so that the capacitor can discharge once that switch opens. So what I meant for the solution to be was something that looked like this. So this is the same circuit, right? 2 micro, 1.5K, and then this opens at 35 milliseconds. You could add another portion to this circuit with a switch that closes at 35 milliseconds and put a resistor here to ground so that when that switch opens, this switch closes and the capacitor can discharge to ground through this resistor. Yes?
This might ruin the entire thing, but couldn't you just add a resistor after the capacitor?
Like without a switch?
Yeah.
That would change pretty much everything about the circuit, because it will now change how this capacitor charges. It will change. Also, if you were to, so basically, I'm cutting off the input, but you're saying put another resistor right here just to ground, basically.
No, like after, so like resistor and then the capacitor and then another resistor after the capacitor before it goes to ground.
Isn't that what I drew?
On the bottom.
Oh, you're saying right here?
Yeah.
Oh yeah, no, that's going to change everything. That's going to change everything. We're going to talk about that today. The reason that's going to change everything is because if that's the case, let's say that is the case, this node is going to want to be 0 volts all the time because it's connected to 0 volts through a resistor. So rather than the capacitor charging the way that we're used to, some different things are going to happen. So we're going to cover that today. But yeah, basically you need to add this path for charges to pour out of the capacitor to ground so that it can discharge. So what's that? Are you trying to figure out what's the difference between this and this?
I get that. I was just saying, like, theoretically, would that still work, even if it changes the entire function of the circuit?
This? No, because the capacitor will still be charged.
Oh, really?
Yeah, I mean, if we were to draw a circuit like this, so what you're saying is like I've got a cap and then I've got a resistor. This changes how the capacitor charges. It's also going to change how the capacitor discharges, and basically in steady state we'll have 0 volts there and we'll have whatever my supply voltage is here. So my voltage across the capacitor will be my supply voltage, just like we're used to. But I mean, yeah, I basically said to do this without. This isn't going to discharge the capacitor. Basically, it's not. The capacitor will charge even with this resistor here. So you need a path for the charges that basically built up on the plate to pour out, and so that it can basically restabilize. What was your question?
Does it need a resistor after the switch?
So if you were to not put a resistor here, that's basically the same thing as saying a resistance of 0, right? And so when the switch closes, my current that's going to flow through this switch, this current, I could call it I, it would basically be whatever my capacitor voltage was minus 0 over 0. So ideally, in this case, it would be an infinite current, and you don't want that. That can cause some serious issues. Because then my RC, right, is 0 also, which means it discharges instantly, and that theoretically can't happen. So even in real life, if you were to do this switch has some series resistance. Its resistance is not 0.
So does the wire.
And so does the wire. So it will never discharge instantaneously, right? Let's say that the switch had a resistance of 0.1 ohms or something, and the wires had like 0.01 ohms. Then my RC would be 2 microfarads times 0.11 ohms, right? It would be the series resistance of this switch and the resistance in the wires. And so you're going to get a really fast discharge, right? It's basically going to be like 0.55 microseconds, but it won't be instant. In an ideal circuit, though, like LT Spice, where everything has 0 resistance, you will get infinite current, and it can cause some simulation problems. So you want to discharge through it like a known resistance. Does that make sense? Like maybe like 1K or something.
Got it.
Yeah.
For my answer, I did not put a resistor. I just said there would be a wire. You could put a wire from, I think that node was VO to ground.
Yeah.
Would that, I guess, just be incorrect? Like, would Abraham just be like, you got to put a resistor, so like maybe like minus or something?
I mean, it's not incorrect. It would discharge
Yeah.
the capacitor.
I didn't know if you were working with ideal or not. I was just like, put a wire.
Yeah, no, that works. That's true that it would discharge, and that's what I asked was discharge it. What I was going for was add a switch with a resistor, but I mean, adding just
I
a.
didn't add a switch either. I just said put a wire.
Oh, well, yeah, I mean, it's not incorrect. It's just not the best possible solution to the problem. It's a solution, right? There's an infinite number of solutions, but yeah, I'm gonna tell him to grade this one easy because this was just meant to get you thinking, right? Yeah.
I basically said you should just put, I guess that's wrong as well, but I'm like, if you just reset VX to 0 and like rounded that after the switch was done.
Yeah, that's what Charles did also. He basically said that instead of the switch opening, have it open to ground so that it'll discharge. And that's true. That will work also. But technically, that's altering components in the circuit. That would be like a whole different switch now.
Right.
That would be a switch that's open at first, then closed, and then connected to ground. So that's like a 3-position switch rather than.
Because the way I read it was you can't remove them, but you can't like change their values either, but you can like work with them. I don't know.
Yeah, I mean, without removing or changing, I basically just meant add some circuitry.
Yeah.
Maybe I should have said that, but I'm just glad you guys were thinking. I wanted you to think about this, and it sounds like you thought. So I got what I wanted out of it. Any other questions about the homework in general? Anybody have problems with A or B? No? 1A or 1B? Yeah.
Or actually, it was on 2.
This one?
So we had a periodic switch. So it's the last number was 50
Oh, yeah, 50
milliseconds.
milliseconds for the period.
So
Right.
Does that include a delay when it repeats again, or is the delay only in the beginning?
It's only in the beginning.
Okay.
So the delay tells me, this is telling me when is this whole process going to start. It's going to start at 10 milliseconds. This is telling me it's going to stay on for 25 milliseconds, and then this is telling me it's going to that process right there is going to repeat every 50 milliseconds. So after the initial 10 millisecond delay, there's not going to be another delay.
Okay.
It'll be on for 25 and off for 25 for the rest of the time.
So then does it switch back on at 60 milliseconds then?
Yeah, it would. That's why I ran it for 60 so that you wouldn't see that.
Okay.
Because if I were to run it to like 70 milliseconds, then you would see it switch back on. And in this case, it's not going to do anything because the capacitor is still charged.
Right. Why make it periodic then?
I don't know. I was probably messing around with it and just left the 50 milliseconds there. You could also just not put that part of this SPICE directive, and it would just stay on for 25 milliseconds. But then it wouldn't be periodic. It would shut off after 25 and just stay low.
I think I overanalyzed. I didn't do anything wrong, but I was just like, I sat there and thought for like 4 minutes, like, why is this? So.
Yeah, sorry. It was just there because that's just what I put. But, yeah, since it stops at 60, I figured it wouldn't matter. What's up?
I may have ran into an issue with the sim because my VX just never went down. It never went back down to 0, and I thought that was really confusing.
It's not supposed to go back down.
It's not supposed to go back down.
It's
right?
The
it's
capacitor's charged and it just
Right, it's supposed to stay up.
Yeah.
Okay, cool. Just
yes,
making sure.
because this voltage is going to be at 12 volts when the switch opens, right? And since there's nowhere for current to flow, this current through this resistor is 0, which makes VX still 12 volts.
Right, that's what I stated. I was like, if you put ZX to 0, then it should go away. Okay.
Yeah. So
Because
that's
that's what I was a little confused on.
yeah. No, that's all good. That's how it's supposed to work. All right, everybody good with everything then? All right, I want to look at a different like view of an RC circuit with a little bit different configuration that we're going to need to talk about today in order to kind of solidify your understanding of what's happening in these circuits. So I'm basically going to do the same thing we did yesterday, except this time I'm going to switch where the resistor is and where the capacitor is in the circuit, and it's going to get a little more in depth about what's happening here. Okay, so if I were to draw the circuit like this instead, this is going to be, this is also just an RC circuit, except the components are flipped. And so the way things happen in this circuit is going to be different than what happened in the previous circuit, but the concepts stay the same. So before I even get into what's going to happen in this circuit, I want to look at this equation. All right, so I haven't said this yet, but it's true that capacitors cannot charge or discharge instantaneously, and that's because of this equation, right? Basically, charging or discharging a capacitor requires changing the voltage across the capacitor, because charges are pouring in or out, and we know that CV equals Q. That's another equation that we know. But looking at this equation, if I wanted to charge or discharge a capacitor instantaneously, that would mean I would have to change the voltage across the capacitor in 0 time, right? That's what instantaneous means. It means it happens in 0 time. It requires no time to happen. And so if I sent this term dt, the difference in time, to 0, would everyone agree that my current would be infinite? That cannot happen in real life. Okay? So the general rule about capacitors is that the voltage across a cap cannot, this is very important, the voltage across the cap, it's not, this node can change instantaneously, this node can change instantaneously too, but the total voltage, if the voltage across the capacitor is 5 volts at one instant, it cannot be something else in the next instant. It has to require some time to change voltage. So the voltage across a cap cannot change instantaneously. That concept is going to drive how this circuit works, okay? So let's look at a circuit, an example of what would happen in this RC circuit. Let's say I start at a value of 0 and I charge up to a value of, say, 10 volts. Let's let this be 1 microfarad and this be 1 kilo ohm, just to make it easy. What's my tau? 1 what? Millisecond. Okay. Let's call this V in, and let's call this V out. And then I'll plot V in. Here, you know what? Let's just section this off. We're going to plot, again, V in and V out like we did on the homework. Okay, that's what's going to happen here. So I'll plot V in over here, and I'll plot V out over here. All right, and I want to do one more thing. Let's add a time delay of like 3 milliseconds. So let's say that this pulses from 0 to 10 at 3 milliseconds, okay? So if I were to draw my input, I'm going to go 1, 2, 3 milliseconds, and it's going to jump from 0 to 10, and it's just going to stay there, right? 10 volts. Everybody's cool with that? Okay. So now, the question is, what's going to happen to V out? You might think it's going to charge the same way that we saw previously, but it's not, and I'm going to tell you why. I just changed V in from 0 to 10 instantaneously, ideally, right? In simulations, it's 1 picosecond, but it's basically instantaneous. So if I jump from 0 to 10 on the input, what was the initial voltage? Well, I guess I didn't give it. Let's say that VC initially is 0 volts. So initially, there's no voltage across my capacitor. The capacitor is discharged. So when this node V in of t jumps up to 10 volts, if I were to keep this V out at 0, that would mean I just changed the voltage across the capacitor instantaneously, right? It can't stay at 0, because that would mean that I went in one instant from no voltage across the capacitor to 10 volts across the capacitor. Okay? So instead what happens is over here at 3 milliseconds, my node V out is going to jump up to 10 with my input. And the reason it's going to do that is because now at this instant, my voltage across the capacitor is still 0, right? This node went up to 10. This node went up to 10 with it, right? So the voltage difference there is 10 volts minus 10 volts, which is still 0. That's okay. These nodes can move instantaneously. The difference across the capacitor cannot, because that would mean we dumped charge on the capacitor in an instant. Okay? And so now what starts to happen is the capacitor, the V out node will discharge down to 0, like, bless you, like what we're used to seeing. What did I say my time constant was? Okay, I drew that horribly. Bless you. So this would be, it would take 5 time constants, so we'd be at 8 milliseconds. And this would be 99% discharged. So notice the this is not the capacitor voltage. The capacitor voltage is the difference between these two. So as that node, V out, is getting dragged down to 0, the capacitor is charging, because one side of it's at 10 and the other side of it is going down. So at the end here, at 8 milliseconds, the capacitor voltage is basically 10 volts, roughly. I'm sure there's questions. Does anybody have any questions about this? Yes.
But that doesn't take into account the voltage drop over the resistor.
Well,
Voltage drop in this case?
there will be, yeah. So initially the voltage across the resistor will be 10 when it pulses up.
Right. So the voltage drop would be 10 across the resistor?
At this instant,
At that instant.
yes. And then that voltage drop is going to continuously drop. It's going to be getting smaller and smaller and smaller until, because basically what happens is this pulses up to 10 volts, right? This node goes up to 10. This node is at 0 because it's connected to ground through a resistor, okay? And so because of the capacitor's properties, it cannot change its voltage instantaneously. So this node jumps up to 10 with the input. But now, again, after that moment, we still have this node tied to 0 through a resistor. So it wants to go back down to 0. And the way that it discharges is based on the capacitor's equations. So I want to run this in SPICE just so you can see.
So what is causing V out to jump up to 10 volts? Am I just saying that's what's happening?
No, that's literally what's
Is
happening.
that what would happen in a physical circuit?
That's what would happen in a physical circuit. And what's causing V out to jump up is that it's just, this is like the laws of the physical properties of the capacitor. The capacitor's voltage cannot change instantaneously, because that would mean that we generated an electric field instantaneously, and that would mean that we dumped charge onto the capacitor in 0 time. We dumped some amount, I guess in this case, since it's 1 microfarad and 10 volts would be 10 microcoulombs, got dumped onto the capacitor in no time. And it definitely takes time for these things to happen. So by the nature of electronics and how they work physically, that node jumps up to 10 with the input.
Does the 10 volts come up from ground?
Does it come from ground?
Yeah.
Do you mean like does it start at ground and then jump up, or are you asking where is it coming from?
Where does the charge difference come from?
Because wouldn't charge have to move through the capacitor in order to get V out to go up with V in?
Yeah, but when the charge on the capacitor is 0, it's essentially just acting as a wire until some current gets pushed through it, correct?
So yeah, so basically what we say, and I haven't even gotten to this yet, is we say that capacitors act like a short during AC, during alternating current, or during what we call a fast edge. This would be called a fast edge. And capacitors act like a short when there's a fast edge. Okay? So initially, I said last time, right, a capacitor acts like an open during DC, right? It acts like an open. No current will flow through it. But during AC, it acts like a short, okay? So for that brief moment where this flies from 0 to 10 in a really quick moment, this node does the same thing because this is acting like a short. So that node does the exact same thing. It basically goes...
And then it starts charging.
So yeah, so basically nothing's actually going through the capacitor. That's the one thing we have to note, right? A capacitor is 2 plates separated by some dielectric, right? So nothing's actually going through the capacitor. But there is an electric field that we would have to basically form that electric field instantly if we assume that this voltage stayed at 10. And since this side goes up to 10, and since the capacitor acts like a short, this guy goes up to 10 with it.
Okay.
And another thing that's important to note is that 10 volts, that's not a driving 10 volts. Like, we couldn't connect that 10 volts somewhere and power something. But what we would read if we put a multimeter there is we would read 10 volts because of the properties of the capacitor. Okay? This side's being driven to 10 volts by the source. This side is not being driven to 10 volts. It's getting pulled up to 10 volts because of the properties of the capacitor.
But my capacitor doesn't explode when I do that?
No. Because the voltage across the capacitor is not changing. It's staying at 0.
So
So that's the reason it doesn't explode.
That's the reason it doesn't explode.
So V in and V out are changing at the same rate at the same time until they reach whatever the 10 volts is.
Exactly.
Then the capacitor starts.
And then the capacitor starts charging.
Okay.
Exactly.
Oh, that's like the opposite of an inductor in DC then, when it comes to current.
Inductors and capacitors are basically like, they're almost like inverse components of one another, because this is how an inductor works for current,
Yeah.
and this is how a capacitor works for voltage. So we're going to get into inductors, obviously, in the probably next week. This guy's a question. Yeah, what's up?
Could you explain why the VL node drops down just because it's connected to ground? Why does it exactly go down to 0?
Why does this go down? Because now the capacitor is charging.
Is it because the equation for I, the difference in voltage and I,
So yeah, basically, what's going to happen is, here's what's going to happen. I might need a new sheet of paper. Let me get a new sheet of paper. Let me just redraw this. I don't want to draw on top of this one. All right. Oh, whoops. You know what? I'm not even going to do this. I don't want to deal with scribbling stuff. All right. So, this is initially, I'm going to use a couple different colors here to just show everything. This is initially at 0, right? It's connected to ground through a resistor, and when everything's stable in a DC circuit, right, which it is before this switch, this voltage jumps up, no current can flow because the capacitor acts like an open, right? So this is at 0 volts. This is also at 0 volts. However, this thing pulses up to 10 at some point, some time. I think I said 3 milliseconds in the previous case. This is going to go up with it to 10 volts, right? And now, at that moment, this voltage is 10 volts and this voltage is 0 volts, right? So I'm going to get some current that's going to flow through this resistor, okay? When I get a current that flows through this resistor, it's going to start pulling this node down, okay? It's going to start pulling its voltage down. So let's say initially, what did I have over there, 1K? My I is going to be 10 milliamps right off the bat. But now I have a current that's flowing through my capacitor. And now I know that that's equal to C dV dt. Okay? So that means that if I divide by C, so in this case 10 milliamps divided by, 1 microfarad, I get some change in the voltage across my capacitor. But this node can't change. It's sitting at 10 volts. It's connected to a power source. This node is free to move. So it starts dropping. Right? That voltage starts dropping because I'm pulling a current through the capacitor. And so let's say it drops down just a little bit to 9.8 volts. Okay? Now I have a lesser current flowing. So it's going to still pull more charge off that capacitor. And basically that behavior is defined by, it jumps up to 10 and then it starts discharging at the rate of the capacitor discharge equation. Does that make sense?
Yeah.
So it would go, this was 3 milliseconds, and then this might be 8 milliseconds. Takes about 5 tau to discharge 99%, right? But that's what's happening there. What's happening is that I'm pulling a current because this is at 10 and this is at 0. That current results in a change in voltage across my capacitor, but this node can't change, so this one has to. And then in steady state, again, we have 10 volts across the capacitor, basically. So I have my charged capacitor, where this side is being kept at 10 volts by a source, and this side is sitting at 0 volts because it's connected to ground through a resistor. So what's interesting to us is what happens when the switching occurs, right? Before and after, it makes sense. It makes sense that this would be 0. It makes sense that this would be 10. But the question is, how does it get there? And this is how it gets there. Okay, any questions about that before I do this in Spice real quick?
So when your capacitor starts charging, which direction does the current flow?
It's flowing this way. The current is flowing this way.
So, but you have the same potential on either side if there's 10 volts on either side of the capacitor.
Only for a very brief moment do I have 10 volts. Only for literally an instant do I have 10 volts here and 10 volts here. Immediately, once I get 10 volts here, a current starts flowing through this 1K,
Okay.
and it starts pulling.
Resistor to ground.
Exactly. And then the capacitor current starts flowing.
Okay.
All right? Yeah, he had a question first.
That symbol on that power supply is just like, that's the fast name symbol.
Right, it's not like in Spice or anything like that. I just draw it like that because plus minus just, I don't know. It's not as satisfying.
It's kind of cool looking.
This?
Yeah.
Yeah, I like this better for and then if it's like a falling edge, like we'll draw it like this. And then sine waves, you know, we draw them like this.
For AC.
Yeah, all these different sources. They don't have those in Spice, but as engineers, we like to draw them so we know what we're looking at.
Makes sense.
You have a question?
Yeah, so, I don't know, I'm just trying to visualize this in my head in a way that works idea to do, but is it in a way like, at the start, it's just a wire, and then like, as it like, so it's just a wire, it's just a short, but then as it starts to gain charge, it kind of becomes a resistor in a way, like, well, it doesn't become a resistor, but it acts as a resistor.
You talking about the capacitor?
Yeah, the capacitor. And it kind of increases its resistance until it gets to 0 in a way. I don't know, like I'm just.
Oh yeah, you could. I guess you could think of it that way. You could think of it that way. You're saying it starts with a short, and then as it moves, as current, it starts to charge. It moves back towards being an open.
Yeah.
Yeah, that's what. I mean, that is what's happening. Yeah, but it's not acting like it's not a resistor in any way. I mean, it has some.
I'm not saying it is.
Yeah. But you can think of it that way.
Okay. Cool.
But I would say it's probably better to think of what's happening with the actual resistor, because I don't know that that's actually what's happening physically. I know what is actually happening is that if I have a voltage difference across my resistor, Ohm's law kicks in and I get current flow.
Right.
And then as my capacitor starts to charge, that means that the difference in the capacitor voltage has to go up, which means this node has to go down, and then that current gets lesser and lesser and lesser until there's 0 current flowing in the circuit again.
So rather than the capacitor kind of reducing the amount of voltage, it's kind of like reducing the amount of current that's getting flowed through? Because it's basically just building up electrons on each side. So
It's
like a pipe, it's just basically building up until it's completely clogged in a way.
Yeah. I mean, however you want to think of it, as long as you get these right, I don't really care how you think of it. Yeah, I mean, this stuff's challenging. I'm not going to pretend like it's not. When I took this class, I thought that this stuff was challenging. But let's just go ahead and throw this in Spice real quick, just so we can show. Uh, 0, 10. I said 3 milliseconds, right? Go 1 pico, 1 pico. And so what you guys would see, right? What you would see is if I change these rise times to something really long, like 1 millisecond, none of this would hold true. This is all assuming that the edge is really, really, really fast. Okay? Everything would change if the edge wasn't really fast. So that's why I tell you to put 1 pico. Because typical, like, supplies, and when you have bits moving around inside of electronics, and you have function generators that generate these signals, it'll say in the manual somewhere that like the rise time is between 20 and 40 picoseconds. It's like a ridiculously fast rise time. I just put 1 pico because it's easier than typing 20 or 40.
Kind of like when you turn on the light switch, it doesn't take more than half a second.
Well, that happens at the speed of light,
Yeah.
but that's because of some other crap. That's way deeper than anything that I'm gonna even try to explain. The reason why electricity, nothing's actually moving at the speed of light, but the process happens at the speed of light.
Oh yeah, it's really cool because charge movement moves at the speed of light, but the particles that are actually moving to create those charges move like exceptionally slow. Like,
Yeah,
ridiculously
that's
slow.
called electron drift.
Yeah.
Yeah, and it's all this stuff that you learn in physics.
It's super wacky.
Yeah, it's a lot. It's a lot to think
Kinda
about.
like that whole stupid thing where it's like you don't look at a particle, it acts as a wave, but when you look at a particle, it acts as a particle.
No, it's just because like the particles themselves, their motive forces are like ridiculously low. It's like 10 to the negative like 19 or something like that. So the particles, the electrons themselves are moving really slow, but the electrical impulses between them are moving at the speed of light.
Yeah.
Basically, you have to look at the space in between the electrons rather than looking at the electrons themselves.
Yes.
We go over it in physics. It's super weird.
All right, here I'm plotting this, guys. V in 0 to 10, 3 milliseconds. Nothing interesting, right? But V out does exactly what I said it would. Are you impressed?
I'm impressed.
I'm just kidding. All right. So, yeah. So you see, and then let's plot the current. There's the current. It looks very similar, right? Because, like I said, at that instant when this jumps up to 10, the current through that resistor is going to jump up to 10 milliamps. And then as that current flows, it pulls this node down a little bit because it's charging the capacitor by pulling a current through, this plate of the capacitor, basically. What's happening is charges are moving onto that plate. It's charging. And so as that voltage starts dropping, the current starts dropping with it, and you get this behavior. Yeah.
How do you get the line?
How do I get them to be this thick?
Yeah. Because mine are.
They're in tin tool.
If you go to this control panel, and then drafting options,
It's under waveforms actually.
oh, waveforms. You can get data trace width, so you can make it as thick or as thin as you want. If I do like 1, it gets really thin and it's really hard to see. So I think I leave it on 5. Oh. Yeah, so that's how that's done. Okay, any questions about this? Yeah. Like the current? It's going to be the same. Well, I'd have to flip the capacitor. Hold on. Let me run it again. So it's the same current because it's in series, right? These two components are in series. Even though it's not a resistor, the resistor is basically causing the current flow, and the capacitor has to follow suit. You can't have different current flowing here than you have flowing here if they're in the same loop, right?
What did you say the name of the current flowing through the capacitor was? There's like a special name for it because.
Oh, it's called displacement current.
That's what it was.
I was going to say I have a weird comparison. Basically, it's like if you have a balloon, fill it up with a tank of helium instantly, so then you slowly let it dissipate. And so that's what the curve is doing.
Yeah. I mean, there's a lot of different analogies. You can think, a lot of people like to think of it like a bucket of water. Like you can't fill the bucket instantly. Doesn't matter how big of a hose you have, it's still going to take some time to get the water into the bucket, right? And then when you poke a giant hole in the bucket or you dump the bucket, it won't come out instantaneously. There is some time required to get that water out of the bucket, right? That's another analogy that a lot of people like. However you want to think about this stuff and get yourself to understand it, that's totally fine. Eventually you're going to get to the point where you don't need any kind of, analogy to understand it. You're just going to accept that that's just the way that it is.
The world is messy.
He had the next question.
What would make a capacitor explode?
Okay, so there's a couple of different things. So capacitors have what's called a voltage rating. I think I put that on your last homework. That voltage rating multiplied by the capacitance is basically telling you how much charge that capacitor can store. If you exceed that voltage rating, you're basically putting more charge on it than it can handle, and it'll pop. And it's happened. I've seen it in the lab. Yeah.
Is the blowing up basically electrons going through the dielectric?
Yes.
I don't know. Maybe it could be.
It's a discharge between the two plates. So like the dielectric the resistance between the dielectric is too much, and then it actually arcs through it, and then that's why it pops. Yeah.
I know that in Electro Boom's video, he had that happen where he put way too much voltage on the capacitor, and he just had these like little sparks of energy like popping through the plates, and he talks about how it basically shorted the two plates together through the dielectric. Like there was too much voltage for the dielectric to handle anymore, and so the electricity was just like, all right, we're going to go right through it. Obviously, it's not thinking, but yeah, what's up?
I could be wrong on this one, but if you change the resistance to 2K, would that drop the current from across that to 5 amps, right?
Yeah.
And then would that change the current that's going through the capacitor, or?
Yeah, that would change everything. So that's what this is going to change is now the tau is going to be longer. It's 2 microseconds instead of, or 2 milliseconds instead of 1 millisecond.
Oh, right, yeah.
And it's going to go down to 5 milliamps. So let's run it. And so you see how it got a little, did you see how it got a little longer? Here, you know what else we can do? Let me see if I remember how to do this. Dot step param R1 1K 3K 1K. I don't know if this is going to work. What this should do if I did it right is it'll step this value from 1K to 3K in steps of 1K, and it'll plot all of them. So let's see if it actually does it. Hang on. Don't get mad at it yet. Okay, I'm mad at it. I don't know what it did. I don't remember how to do the step parameter. I'll have to learn that and show it to you guys because it's useful. I thought it should have worked. I still think it worked. Let me see something. R1 linear, start at 1, stop at 3, increment by 1. Look, I knew I was right. But why isn't it working? Here, let's get rid of some of these.
You have R1 and 2.
It could be because I have too much stuff being plotted. Let me delete some of these panes. And let's just plot these two things. Okay, let's not plot those two things. Let's just plot V out. What the hell?
Does it say the time between it?
It should be fine. It should run. What it does typically is it'll plot several different waveforms in several different colors, so you can look at all of them. I'm not entirely sure why it's not doing that. Oh, I know why. You have to make this a. I'm sorry. You have to make this a parameter. So I would call this R out, I guess. And then I will step R out. That's why. Now let's run it. There you go. All right, so there you go. So now you see, let me add another pane and let's go with the current. So you see how the current is initially 10 milliamps. Here, let me do one more thing. I think you can pull up like a legend. View, plot settings, select steps. No, that's not what I want. Window. I know there's a way. You guys see a legend anywhere? Nope.
Yeah, there's one sitting at the computer.
Wow, that was awesome. Thanks. It's here. You right click on the plot, view, and then step legend.
Okay, cool.
So interestingly enough, the colors don't match. I'm not entirely sure why. Let's run it again and see if it works out. Because that's just wow. Okay, that's useless. Sorry. Okay, but first, okay, let's just look at it. So the blue is my that's my 1K. My resistor was 1K. So it takes. Here, let's run it for a little longer so we can see some more interesting stuff. So if it was going to take 3 milliseconds, then that would be 15. So I need at least 18. So let's just do 20. All right, there. So you note initially this is going to jump up to 10 volts, right? And I have 1K, so that's going to give me 10 milliamps flowing initially, and then it's going to discharge at the rate of the capacitor. So if you wanted to figure out what this current equation was, or the V out equation, you're going to use that discharging equation, right? Anytime that it's going from some value down to something, you're going to use the discharging equation, and anytime it's going up, you're going to use the charging equation, okay? So now, if it goes to 2K, my current gets halved, right? It's 10 volts over 2K, so it's going to go down to 5 milliamps here. Hold on. Can you see that? Let me, all right, so it goes down to 5 milliamps when it jumps, but now it takes longer to discharge than the blue one does, you see? And then this 3K would give me 3.33 milliamps or whatever, and now that's going to take even longer to discharge. Okay, so you see tau changing, but you also see the current changing. Anybody have any questions about this? Yeah.
So it's basically what you're showing us with capacitors right now is that the order of where you have your voltage, your capacitor, and your resistor matters. If you have a voltage, resistor, capacitor, then it's going to be the charging, and it's going to be capacitor, resistor, voltage, it's going to be discharging.
For finding V out. If that's what if you're
Yeah.
talking about this particular node, then yes.
Yeah.
And that's because in either of those cases, the capacitor's charging. It's just that in this case, this node is not free to move around. It's tied to an input, so it goes 0 to 10. So in order for the capacitor to charge how it wants to charge, this node is the one that has to move like that, right? It's free to move because it's just floating over here on the right-hand side. It's not tied to any source, okay? So that node will discharge, but you would not say in this case that the capacitor is discharging. The capacitor is charging. And so if I wanted my capacitor, so another interesting thing that's going to happen here, I want to give you time to take the quiz, obviously, so I have about 13 minutes. But what's going to happen basically when I send this input back down to 0, right? What's going to happen? Because so that's what I'm going to talk about next. Once we stop with the questions, I'll give like 2 more minutes for a couple. If anyone has any more questions about what's happening here, but just so you know, like you said, if you have it configured where it goes source, capacitor, resistor, you just have to note that this side is tied to the input voltage. So what's going to be wiggling around is this voltage. Where in the other case, I have a resistor and my capacitor is over here. That capacitor output voltage is what's free to move, so that's why it charges this way. Because the other side of the resistor is what's connected to an input. So you're right to think that way, but also keep in mind that the concepts are the same between the two circuits. It just got a little deeper here because now we're being exposed to another possibility. Okay? So just note that the capacitor is still charging here. Anytime the capacitor voltage is going from some smaller value to a larger value, in this case 0 to 10, the capacitor is charging. Yeah.
Can you make SPICE plot changes in tau for you if you're sweeping through different resistor values?
Like actually physically plot
Or like
that value?
calculate what that value is for you? I mean, you could.
I think you can.
You can do the math, but can you make SPICE do it for you?
I think you could. Let's see. Let's try something. I'm going to try and see. Add traces. Nah. They only give you the option to plot voltages and currents. But I know over here in this window, there are other things you can do. Like there's .tran, .step, .dc. There's all these different things you can do. You can do like a .measure or a .calculate that will calculate whatever you want for you. I'm not sure where it shows it though. I think it'll pop up in a little error window, like how when we did the DC simulations. Yeah. I think it pops up in there. I'm not super familiar with running those sims, but if you want to do more like looking into that, you can do that.
Okay.
There's all these different, you can do .measure, you can do .integrate, you can do .derive. It'll take derivatives and integrals. It'll find the area under these curves if you do the integral, right? It does all this crazy stuff. I'm just not super familiar with using that. I know that you can though. Okay. All right. So now, since we have about 10 more minutes, I want to show what's going to happen when we discharge this capacitor. Okay. So this is going to be interesting. Let me cut this in half. I don't want to waste more paper. So now we're sitting here in steady state, right? My capacitor is going to be charged. So what I'm going to draw is I'm going to draw the other type of source when it's a falling edge, right? It's going to go from 10 down to 0. My capacitor is initially charged to 10 volts, right? This node is going to be sitting at 0, and I've got a resistor here. Okay, so this is at 10, this is at 0, this is 1K, and this is 1 micro, right? Okay, so here I am sitting here somewhere way down this plot where my voltage I guess this is V out, and this was V in. My V out is basically 0. Okay, now let's draw some plots. What is going to happen? Can anybody guess or give me, let me just get the question out before someone says something. If I have my input, which is at 10, let's say out here somewhere at like 20 milliseconds, we're like way later down this plot, okay? So this is like a continuation of this plot. My input is going to go from 10 down to 0. Okay? So it was at 10, it just dropped to 0 volts. That's this node, it's dropping to 0. So now, let me change colors. It just went from 10 down to sitting at 0. What's going to happen to the output node? Does anybody have any ideas? Hold on, what was that? What was that? There will be current. There will actually be current. And there's a reason for it. What were you going to say?
It'll be identical to before.
This?
Jump to 10, and then
You're on the right track, but you're not correct.
It would go up to negative 10, correct?
Yes.
It goes to, so technically go down to negative 10.
It goes down to negative 10.
Function up to 0.
Exactly. It goes like this. And the reason is we need to maintain 10 volts across the capacitor, right? We can't change instantaneously. So when this jumps down to 0, this has to shoot down to negative 10 to maintain 10 volts across the capacitor, right? Okay, does that make sense to everybody?
So essentially, when it drops down to 0, it's essentially like the current is suddenly being switched into the other direction.
Well, initially, when it's sitting here in this steady state, there's no current flowing. It's sitting here at 10. This is at 0. No current flows in the circuit. But when I jump down to negative 10, well, when I shift this down to 0, my capacitor voltage was 10 volts. And so if this side gets pulled down to 0, in order to maintain a 10 volt difference across the capacitor, this voltage shoots down to negative 10 to keep that 10 volts. But now, since this voltage is shot down to negative 10, and I have 0 down here, I get a current flowing this way. Okay, and that current results in my dVdt, right? That's my I equals C dVdt, but going the other way. We're basically discharging the capacitor now. We're putting all the charges back on the capacitor, discharging it. All the charges that were displaced. Yeah?
What's the time for that?
The time?
Yeah, on the graph.
This one? It's roughly 5 tau.
Or for, I think it says 20.
Oh, 20 milliseconds?
Yeah.
Yeah, it's 20 milliseconds. I just picked some arbitrary time that was, if we were like looking at a continuation of this plot, some arbitrary time. So here, let's go do that in simulation. How much time do I have? 6 minutes? All right. So in sim, I would go back here. If I wanted it to pulse back down at 20, I would make my T on 17 milliseconds. Everybody see that? Because now it pulsed up at 3, and then 17 milliseconds later, it's going to drop back down, okay? And then I just won't put a period, like you said, right? So now we run it, and let me run it for, I don't know, let's say 40 milliseconds so we can see it all happen. Let's get rid of this sim and put this back to just being 1K. And there you go. So hold on, let me just do my V in and my V out. So you see V in, right? It goes 0 to 10, and I get that action like we talked about. It jumps up to 10, and this comes back down. And then, so during this whole time from like 8 milliseconds out to 20, or like 19.999, everything's stable. I have no current flowing. So if I plot the current during that time, it's 0. You see that? 0 milliamps on this right side over here. But after my my voltage comes back down on the input, I need to maintain that 10 volts across the cap. So this voltage V out shoots down to negative 10. I get a current flowing in the other direction. So again, right, my current was initially flowing in one direction to charge the capacitor, is now flowing in the other direction to discharge the capacitor, and then we reach steady state again. Any questions? Do you have a question?
No, I get it, because although they both rise, the one dissipates, the V out dissipates. But then in order to reach zero, it still needs to take 10 distance. So it just quickly dips down and comes back up slowly.
That's right.
It's maintaining equilibrium, basically.
And the amount that it dips down is the same as the amount of change in V in.
Exactly, because it needs to keep the voltage across the capacitor. This changed by 10, this changes by 10. If this were to drop down to some crazy like negative 150 volts, this would have to go down to negative 140 volts to keep that 10 volts across it, or negative 160 volts. It has to just maintain the voltage difference across the capacitor.
Correct.
Were you going to ask something?
Yeah, I was going to ask this. Like, I think the answer is no, but is this like some? Would you use a capacitor in like a light dimming system, where you like dim the light and increase the light by like?
You can.
You can.
But this would be very not a very good idea, because you won't be able to control the dimming. It will just dim at RC times 5.
Well, I mean,
Like, it's not going to be a controllable dimmer, basically.
So basically, you'd turn your light on, it would get bright, and then it would just get dim again.
Yeah, if you were to connect the output of this to a light, you would see it dim if you made the time constant long enough that we could actually like view it with our eyes. Right at these times, like in milliseconds, you're not going to see anything. You're just going to see on and off. But if you were to make a big cap and a big resistor and plug this into a light, what you would see is you would see like bright and then like dimming until it's off. And a lot of times you do see that. I don't know if you guys have ever like worked with trying to think what board it is. Some of those like power, like the FPGAs that we have, there's like a power switch and it has like an LED, or even any like wall regulator that you plug in. If you plug it in and then you unplug it, you're like, whoa, why is the light still on? I just disconnected power. It's because the capacitors are still charged and they're discharging through the resistance of the system. Have you ever seen that? Yeah. That's what's happening. So like, for example, when I unplug my charger, it's still charging my laptop for a second. Like, it's not, because right now it's receiving power from the city power, but when I unplug it, there's a lot of capacitors and stuff inside this brick that are still charged, and that charge is still being dumped the only place that it can be dumped. It can't be dumped that way. It can't be dumped into the open, right? It gets dumped into my laptop, so this light on the side of my laptop stays on for a second, and then it eventually dims to nothing, and that's what's happening. This is what's happening. Yeah. No, I mean, no. Well, this might stay charged, yeah. Yeah, it'll stay charged. It'll eventually discharge through the other resistances that are inside the brick. But you won't see the light on the laptop, obviously, because nothing's supplying anything, right?
I know there's sometimes lights on the power supply, and we unplug it from out, and she'll just, the light will stay on.
Yeah. That's because there's still some cap in there that's charged, and it has to dissipate through something. And if it's not connected to any resistors, I mean, if it's on a circuit board at all, it's connected to something. It can't just be sitting there floating. So it'll eventually discharge through whatever's around it, because everything has resistance. But say you have like a capacitor in a PCB or like a circuit board, and it's not connected to any actual resistor in there. It's just sitting on the board somewhere, and it was charged for some reason. The board around it might be like 10 mega ohms of resistance or some huge resistance. So the discharge time will be several seconds, and you'll see it. That's why. But if it's actually connected to a resistor, like in this case, you wouldn't see it. It'll just go off immediately.
If you physically disconnect the capacitor from a circuit after you charge it, will it just sit there and stay charged?
Yeah. And then if you touch it, you could get shocked.
So it'll
discharge through you.
Uh-huh.
Yeah. It's trying to discharge. The electricity always wants to go somewhere, but if you don't give it a place to go, it won't go anywhere. All right, everybody good? I'm going to give the quiz now. This is significantly more challenging than the quiz, so don't get tripped up by the quiz. The quiz is just like your homework. All right?